Okay, next statement of the question. And notice there's one typo in it. In the part C, there's an expression there, and use EC squared minus PC squared. Should be M squared. But also, as I go through the solution, I'll be reinserting factors of C, the speed of light. Okay, so let's set it up. Now, part A says we write down the equations of conservation of energy and momentum. What I've done here is done it in a four-vector method, or four vectors, actually two vectors, if you will. But just as in your ordinary physics course, you want to conserve by component. So the zero component of the four vector, which is the energy expression, and then the, say, x component, if you will, which is going to be the momentum conservation. Here I stuck in factors of c to make sure that this is an energy momentum four vector that has the same units. But of course, as we proceed, we'll go through and actually just write it in terms of the equations themselves. And then in this expression here, the p's are scalars. And by the statement of the question, PB, the photon, the momentum of the photon, is going to the left, which is negative. All other particles are going to the right, which are positive. So these are all now, all the variables are positive integers now. Okay, so the first part, or part A, that's just essentially what we did right there. Part B asks to use the expression for the energy of a photon to insert that and modify this expression as necessary. And that's pretty straightforward because there's two photons in this story, which is B, and so this term here becomes minus B there, and of course PDC becomes ED. So that's simplified. You know, we don't have as many variables, but we see that we'll still have PA and PC going forward. But however, note that as we go forward, we're going to try to express everything in terms of energy as best we can in the end. But for as the question suggests, we keep the memento around for PA and PC. But again, part C, we're told. Part C, we're told to isolate, because we don't care about particle C in this story. We isolate the energy momenta for C and then square it and use the expression as mentioned in the question, EC squared minus PC squared times C squared is equal to MC squared quantity squared. So what we do then, well, let's just isolate this. We just solve for the particle C, just like that. Just solving those components. And now we square. So first we'll square the EC squared, and this is what we get. Again, this is straightforward, just examining the square root of the above. And we do the same for PC, but we're going to add a minus sign because that's what we're going to want to do. We're going to take the first row and subtract the second. And again, note that's what we get. So we carry that out, and again, what we're going to immediately note is if we add these two, so if we add these two, or EC squared minus PC squared, that's equal to MC squared quantity squared. So we get, so that side of the equation becomes MC squared quantity squared. Now, just adding, or adding these two, we get the following. So this is just putting the terms back in down below for what was the previous two lines. Pretty straightforward, just algebra. But now we notice some things we can clean up. So here, this right here, that's equal to MC squared quantity squared. That's the energy relation for particle A. This one we can square out and isolate. Notice that because it's just a sign flip there, we're going to get the EB squared and ED squared terms from that. Multiplying, they're going to cancel. They're going to subtract out. So we're just going to get the cross terms for that. And this one will just carry out down below. So here we go. So I just put this in. So this becomes this. This is the cross terms for these two. Minus 4. There's two cross terms, so it's minus 4. EB, ED. And then here I rearranged this. Put together the EA and PA terms. Okay, that's it so far. So let's go on. Let's go continue on now, and we'll. There we go. So this is where we were. And let's go to the next line, which is just, again, more just cleaning this up. Notice that we have MC squared quantity squared on both sides. We cancel those. And I divide by 2, and I flip the sign. So we have this expression here. Again, so it's the later parts of those. And we just continue to solve as we go down. So now we want to isolate ED because that's what we're interested in. So I'll pull those terms to the other side. Like that, and did a little bit of algebra there, and let's solve for ED, and this is what we get. So this is what we have. Now again, we could go further and insert the value for PA as the square root of EA squared plus MC squared quantity squared. But this is sufficient for this part of the problem. And actually, it suggests there to keep it in terms of the first power of PA. We could expand this. Actually, it's already in the first power of PA, so we're done there. Okay, so that's our result for part C. Oh, sorry, D, actually. We're already in part D. Okay, now we go the part that's really kind of the stressing part of this problem is, well, let's take the high energy limit. So what it says is we consider the important special case in which the incoming electron is extremely energetic. So this would be an example like at SLAC, Stanford Linear Accelerator Center, where you're accelerating electrons and positrons, and if it happens to collide, you have inverse Compton scattering. Those are extremely high energies. So this is what we get. So that means that EA is much, much greater than MC squared. That's what the limit means. And we can express the momentum back out here. And again, factoring out the A, just because we want to do this expansion, or this limit, we'll factor out EA there. And we get this term here. Now notice we can do this right off the bat. Notice that this square root is going to be approximately 1 in this limit, because the second term is going to, the denominator EA is going to dominate, or it's going to make that term go to 0. Well, let's continue on just to do the algebra here. So we put that back into our expression, all that. So that's just inserting it into the expression above. And now if we take this limit, I mean, we could just setting this square root to 1 is essentially what we're doing. We get EA, 1 plus 1 on the numerator, and denominator, notice we have 1 plus, there's 2 terms of the minus sign difference there, so that term goes away. And we have 2 on the top, 2 on the bottom, and we end up with EA. And this justifies the last statement there, which in the question says, simplify equation part D to show that under these circumstances, the outgoing photon, which is ED, has the energy of the incoming electron, no matter what the energy of the incoming photon, because EB does not appear here at all. And that's it. We're done.